Questions 21 through 25 on the 2019 Grade 10 AMC 10A. A sphere with center O has radius 6. A triangle with sides of length 15, 15, and 24 is situated in space so that each of its sides is tangent to the sphere. What is the distance between O and the plane determined by the triangle? So here's a diagram which I think helps greatly to understand the question. And they have told us that AB is 24, and it's an isosceles triangle, so AC is equal to BC, and those are equal to 15. So we can draw a line down the middle of that isosceles triangle, and because it's isosceles, that line will cut the other side in half. So that means AD and DB will now be half of AB, so 12 and 12 like that. Okay, so now at this point we can figure out the value of CD pretty easily using Pythagoras. CD squared plus DB squared, which is 12 squared, is equal to CB squared, which is 15 squared. So that means CD is going to be equal to 9. Now we can calculate the area of that triangle ABC. ABC has an area 1/2 base times height. The base is 24. The height we just figured out was 9, and that is 108. Now we have a very special formula, and this formula states that if you have any kind of circle like this that is inscribed inside a triangle like this, it's tangent to it inside, the area of that triangle is equivalent to the radius of this circle that's inscribed inside times S, where S is the semi-perimeter. And this is a very helpful formula for this question. The area we just figured out was 108. The radius, that is what we will find out. And the semi-perimeter, well, that's easy to figure out. The perimeter is 15 plus 15 plus 24, and then the semi-perimeter you just divide by 2. So that makes this 108 is equal to R times 30 plus 24 is 54 divided by 2 is 27. So R is equal to 108 over 27. Therefore, R is equal to 4. So now going back to the diagram, we want to figure out this distance right there, and I'll just call that D. We just figured out that, which is the radius of the circle, is 4. And then from O to that point is the radius of the sphere, which they had told me in the question was 6. So now it just boils down to a simple Pythagorean relationship between 4, D, and 6. And when you do this math, you get D is equal to root 20, or 2 root 5. So number 21, the answer is D. Real numbers between 0 and 1 inclusive are chosen in the following manner. A fair coin is flipped. If it lands heads, then it is flipped again, and the chosen number is 0. If the second flip is heads, and 1 if the second flip is tails. On the other hand, if the first coin is tails, then the number is chosen uniformly at random from the closed interval 0, 1. Two random numbers, x and y, are chosen independently in this manner. What is the probability that x minus y absolute value is greater than 0? If there's a heads, we have to flip again. And when we flip a second time, if it's heads, we get a 0. If it's tails, we get a 1. The other scenario is if you flip the first time, you get a tail. And in that case, you're going to choose some number at random from 0 and 1 inclusive. So now let's put in the probabilities. The probability of getting a head is half, and the probability of getting another head is a half. So the probability of getting 2 heads in a row is a half times a half, which is a quarter. Probability of getting a head is a half. Probability of getting a tail is a half. So the probability of getting a head and then a tail is a half times a half, which is a quarter. And now these guys, I'm going to break these up into 2. because that's what's going to help us in the question. We can either choose something that's between 0 and 0.5, or we can choose something that's between 0.5 and 1. And each of these has a probability of a half times a half, which is a quarter. Why? Well, the probability of getting a tails in that first flip is a half, and then the probability of getting this half of the range is a half, so that's why you have to multiply a half by a half. And very similarly, a half to get a tail and a half to get that half of the range. So this is also going to be 1/2 times a half, and that's a quarter. So now what we do is we make a table, and the table will help us figure out this little inequality that x minus y absolute value is greater than a half or not. So let's now fill in the table. We've got x, y, absolute value of x minus y, and then we have the probability that it is going to be greater than a half. So we can fill this out 0, 0, 0, 0. We can have either 1, 1, 1, 1, or we can have these ranges 0 to 0.5, or we can have 0.5 to 1, like that. So let's fill all of these out. So now we got to look at this column right here and figure out what is the absolute value of x minus y, and whether it is going to be our requirement that it's greater than a half or not. So there we go. I just filled out all of the possible values of the absolute value of x minus y for all of those. And some of those are 0, some of those are fixed as 1, some of those are less than a half, and some are greater than a half. But there's two that I put a little asterisk because those are greater than a half the time and less than a half the time. That's why I put a little asterisk there. Now let's figure out the probability, but the only ones we're really interested in are the ones that are greater than a half in this column. So let's just circle those. This one, greater than a half, remember. So this one, that, and then here, 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 and here. Okay, so the probability that, now we have to fill out this column here. The probability is calculated as follows. What is the probability of choosing that x, and what was the probability of choosing that y? The probability of getting that 0 is a quarter, and the probability of getting this 1 is a quarter. So you have to multiply a quarter by a quarter, and that's 1/16. And the same thing here. What was the probability of getting a 0? It was a quarter. What was the probability of getting that range, 0.5 to 1? Well, that's here. It was a quarter. So again, a quarter times a quarter is 16. And as you can probably deduce, it's the same way to get all the other probabilities. But this question is a little tricky because of these guys, this asterisk and that asterisk. In those two scenarios, it's greater than a half only half the time for this range. The other half, it'll be less than a half. So that's why you have to multiply this 1/16 times a half. And you have to multiply this 1/16 by a half. So now let's add them all up. We have 1, 2, 3, 4, 5, and 6 times 1/16. And then we have this guy, which is 1/32. And then this one, which is also 1/32. So this gives me 6/16. This is 2/32, which is 1/16. And that is 7/16. And that is the answer to number 22. 7/16, which would be B. Travis has to babysit the terrible Thompson triplets. Knowing that they love big numbers, Travis devises a counting game for them. first Tad will say the number 1, then Todd must say the next two numbers, 2 and 3. Then Tucker must say the next three numbers, 4, 5, 6. Then Tad must say the next four numbers, 7, 8, 9, 10. And the process continues to rotate through the three children in that order, each saying one more number than the previous child did until the number 10,000 is reached. What is the 2019th number said by Tad? Well, let's make a little systematic way of figuring this out. We have Todd and Tucker. So, for example, he starts off with 1, and then 2, 3 is said by Todd, and then Tucker says 4, 5, and 6. And then it's Tad's turn, and he will say 4 numbers, 7, 8, 9, 10. And then Todd will say 5 numbers, 11, 12, 13, 14, 15. And then Tucker will say 6 numbers, 16, 17, 18, 19, 20, 21, and so on, right? So hopefully you get the idea. And then now we have to sort of figure out a system. Now when it comes back to Tad, he's going to say obviously 7 numbers, so 22, 23, 24, 25, 26, 27, 28. So far, how many numbers has he said? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. He said 12 numbers. And we have to come up with a system of how to figure out, these numbers. Well, he's saying the first number, and then he's going to later say 4 numbers. Then he's going to later say 7 numbers, and so on. And if you keep doing this, you'll find that his next time he says 10 numbers. And then next time he says 13 numbers, and so on. So it keeps going up by 3. So when you add it all up, 1 plus 4 plus 7 plus 10 plus 13, ... right? The question is basically saying you want to get up to 2019 because we want to figure out what is the 2019th number that he says. All right. Well, if that is the case, then we have to add this up. And this is an arithmetic sequence. And the arithmetic sequence has a sum of 2019. And the formula is n over 2 times 2a plus n minus 1d. In this case, we're not sure what n is, so I'll leave that in for now. And a is the first term, which is just 1. So that's going to be 2. And then n minus 1 times d. d is the common difference, and that common difference is clearly 3. So this is what I get. So let's see, when I expand this out, multiply through by 2, and then I'll get 2n plus 3 n squared minus 3n, and that is going to be 4038. And then if you put everything on one side, you get 3n squared minus n minus 4038 equals 0. Now you can do a quadratic here, and when you do, you get 1 plus or minus 1 minus 4, 3 minus 4038, like that, all over 2 times 3. And what that does is it shows us that we've actually got a number that's approximately 36.8. So let's see what happens with 36, and then let's see what happens with 37, because obviously n can't be an integer, so it's got to be somewhere in between. When n is 36, and you plug it back into that formula, you get a sum of 1926. So we're a bit short of 2019. When n is 37, when you plug it in, you get a sum of 2035. So n is obviously 37. And then when you get a sum of 2035, you have to go back by 16 numbers to get the 2019th number. So n is 37, and then of course you will count back 16 numbers to get that 2019, counting back from 2035. All right, I think we're making some pretty decent progress here. So let's see what's the next step. Now we have to actually figure out what is the numerical value of that term, the 2019 term. Well, let's make a little table here, and hopefully that table will explain. So we've got n, the term, and the last term. So for example, when you just start off, you only have 1, right? And it doesn't really matter, the last term is 1. When he starts counting, you remember he's down, Todd is 1, and then the next step is 7, 8, 9, 10. So n sort of represents the steps, I guess. In his second step, he's got 4 terms, these ones. And the last term is 10. In the next step, which I guess I can call the third step, he's got 7 terms, and his last term is 28. So it would be very helpful if I can get some sort of a formula to figure out that last term. And you can very easily. That formula is just basically counting up to that number. To figure out the last term, you would take the number of terms, I'll just call that t, and then multiply by t plus 1, and divide by 2. And that will work. So for example, when you had 7 terms, it would be 7 times 7 plus 1, which is 8, divided by 2, which is 28. And that's how you get the last term. So we actually are going way beyond any such number 1, 2, 3. We're going all the way up till 37. And when we go up to 37, we have to figure out how many terms there are. Well, the terms are going to be as follows. It's an arithmetic sequence of the form a plus n minus 1d. So that's going to be 1 plus n is 37 minus 1, d is 3. So that is what, 36 times 3, which is 108 plus 1, 109. So my t is 109. So the last term using that formula will be 109 times 110 divided by 2. And that is 5995. So that is the 2035th term, I guess, in the sequence or series, whatever. But we have to get the 2019th. So to do that, I just have to count back 16 from this number. And therefore it'd be 5995 minus 16. And that is 5979. 5979, and that would be C for number 23. Let P, Q, and R be the distinct roots of the polynomial x to the power 3 minus 22x squared plus 80x minus 67. There exist real numbers a, b, c such that 1 over s to the power 3 minus 22s squared plus 80s minus 67 is equal to a over s minus p plus b over s minus q plus c over s minus r for all real numbers s, with s not being equal to p, q, and r. What is a? 1 over a plus 1 over b plus 1 over c. Well, let's first concentrate on this polynomial that they gave me, and they told me that the roots are p, q, and r. So that means if I were to factor it, it would be x minus p, x minus q, x minus r, like that. And then I'd like to expand this part just for the sake of seeing what it looks like, and I will just write the one where all the like terms have been collected. It's going to be x to the power 3 minus r minus g minus p x squared plus gr plus pr plus pq x minus pqr. So that is what you get when you expand this whole thing and collect like terms. Okay, so we can always come back to that later. It's just good to have that in case we need it later on in the question. So now let's turn our attention to this one right here. Okay, so we've got 1 over s to the power of 3 minus 22s squared plus 80s minus 67. And that is equal to a over s minus p plus b over s minus q plus c over s minus r. Now, I would like to get a common denominator, and I can do that. It'll be s minus p times s minus q times s minus r. And this side, since p, q, and r are the roots, that can be factored as the same thing. So there we go. And then here we just have a 1. Now, at the numerator section, we have to write the following. It would a over s minus q times s minus r. This would be b times s minus p times s minus r. And then we have c times s minus p times s minus q. Okay. Now, the denominators can go since they're the same, so it just leaves me with 1 is equal to this, and that's pretty much it. So 1 is equal to that whole big long thing. Now, since the denominators are gone, that restriction is no longer needed. It was needed here because they were in the denominator. You can't have a 0 in the denominator. But now that the denominators are gone, that restriction is no longer a requirement. So we can let s equal to p. And when we do, this basically becomes 1 is equal to a times s minus q times s minus r, because everything else vanishes. So that gives me 1 over a is equal to, and I can substitute my value for s being p minus q, p minus r. And very similarly, if you let s equal to q, you get 1 is equal to b times s minus p times s minus r. Everything else vanishes, and we get 1 over b is equal to q minus p times q minus r. And then finally, if s is equal to r, this would be 1 over c is equal to c times, it would be just r minus p times r minus q. All right. So now we want to add them. We want to add 1 over a plus 1 over b plus 1 over c, because that's what we have to figure out in this question, an actual numerical value. So that is going to be, if I add these guys up, p minus q times p minus r plus q minus p times q minus r plus r minus p times r minus q. Okay, so now we have to expand this, and when we do, I'll just expand it out first and collect like terms. And when I do, actually, I get this p squared plus q squared plus r squared minus pr minus qr minus pq. That's what I get. But I have to kind of manipulate this because we want to factor it. So what I'm going to do is I'm going to keep the p squared, q squared, and r squared. But this part, it's sort of like a minus 1. I'm going to write it at 2 minus 3. 2 minus 3 is also minus 1. You see what I mean? So instead of minus PR, it'll be plus 2 PR minus 3 PR. The result is the same, but I'm doing that because I need to factor this to make it look a little bit more helpful. So 2QR, 2PQ, and then of course on this side minus 3QR and minus 3PQ. So now I can factor this. This actually factors very nicely to P plus Q plus R all squared minus 3 PR plus QR plus PQ. Okay, so P plus Q plus R is the sum of the roots. And using Vieta's formula, I'm sure you remember, In a polynomial, the sum of the roots are minus b over a. So if you go back to that polynomial, minus b over a, well, this is b, so minus b over a would be minus 22 over 1, since this is 1. So that's just 22. And that represents the sum of the roots, which is p plus q plus r. So that's 22 right there. And then we get to this guy, PR, QR, PQ. PR plus QR plus PQ. Well, that, if you look at this one right here, is this right here. QR plus PR plus PQ. It's basically the coefficient of the term x, of the x term. And what is the coefficient of the x term? It is right here, 80. 80 is the coefficient. And therefore, this QR, PR, PQ is equal to 80. So that is something we can put right here, 3 times 80. So there we go. We've got a numerical value. When you do this math, you get 244. And that is the value for this 1 over a plus 1 over b plus 1 over c. And therefore, 244 would be choice B for number 24. For how many integers n between 1 and 50 inclusive is n squared minus 1 factorial over n factorial to the power of n an integer? Recall that 0 factorial is equal to 1. Well, let's think about this for a second. Before I dive into this, I just want to mention, if you had n factorial over, say, n squared, well, you could write this as n times n minus 1 factorial, and then the bottom you can break up into n times n. These two n's would cancel, and it would leave you with just n minus 1 factorial over n. So with that in mind, now let's tackle this guy. So that is step 2, n squared minus 1 factorial over n factorial to the power of n. Now for this, I want to make this into a better form. So what I'm going to do is I'm actually going to introduce a couple of things here. I'm going to keep what we have, of course, but then I'm going to introduce an n squared on the top and the bottom like that. When I do that, you'll notice that the top now becomes n squared factorial, very similar to what I did up top. And then the bottom now, we have this n factorial to the power of n times n squared. Okay, I'd like to work with this a little bit more. And the way I'm going to do that is by, again, adding n factorial to the top and bottom. And that will allow me to make a couple more changes. The first change is that I will just combine this one and this one to give me n factorial n plus 1, and then I'll just rearrange that n factorial and put it over n squared, and then this n squared factorial will remain the same. Okay, so now we want this to be an integer. Now, notice that if you just look at this term, that n squared factorial is going to be much greater than n factorial to the power of n plus 1. For example, if you had, say, n is equal to, say, 15, well, this part becomes 15 squared factorial, which is 225 factorial. And that's obviously going to be much greater than 15 factorial to the power of 16. So I'm fairly confident that this part will be an integer, since the numerator is greater than the denominator. So now I have to concentrate on that. And that is the key to the question right here. I've got to concentrate on this guy. So I want that to be an integer. Well, let's see what happens. Remember, my range is from 1 to 50 for n. So let's see what happens with the first few. When n is 1, we get 1. When n is 2, we get 2 over 4. When n is 3, we get 6 over 9. When n is 4, we get 24 over 16. When n is 5, 5 is interesting because I think it's a little bit clearer that when it's a prime number like 5, it'll be 5 factorial over 5 squared, which is 5 times 5. And there's no way that this is going to be an integer because this 5 could cancel out with the first 5, right? But then there's no other 5 in the rest of the factorial, 4 times 3 times 2. So this is not going to be an integer. That's not going to work. How about n equals 6? That is going to be 6 factorial over 36. And that actually gives me 120. And you can keep going like this. And when you do, you hopefully will come to a conclusion that this n factorial over n squared is an integer when n is equal to 1, like we showed here, or n is not equal to 4, right? Because 4 didn't give me a value that works. Or n is not a prime, because for prime numbers it won't work. So basically, all the numbers between 1 and 50 that need to be eliminated are the primes and the 4. So that's pretty much how we're going to do this. So of the 50 numbers between 1 and 50, we get rid of that 4, so that's just one number, that 4. And then everything else that we get rid of is a prime number. And between 1 and 50, if you count them, there are 15 prime numbers. So 50 minus 1 minus 15 is 34. So 34 values of n between 1 and 50 will give this to be an integer, and therefore that whole thing will be an integer because it essentially was a modification of the original formula. And therefore number 25, the answer is D.